Hello everyone, my name is Mark Veff. I am a fourth-year PhD student at the Johannes Gutenberg University in Mainz, Germany. I'm part of the Efficient Computing and Storage group under Professor Andre Brinkmann, and today we'll talk about DelveFS, which is an event-driven semantic file system for object stores. This work was in collaboration with OpenIO, a object store company located in France. And in this talk, I will talk about how we use events to create a semantic file system, and then also present some evaluation with regards to metadata and data performance. Now, data-driven science applications are responsible for a huge part of innovation in both research and industry. Their underlying technologies such as data processing or machine learning techniques usually depend on huge data sets, but at the same time, data collection is increasing rapidly in many fields to the point where data collection is actually outpacing its processing and stored into lakes of data. For example, already in 2014, the European Center for Medium-Range Weather Forecast reached a storage capacity of over 100 petabytes with an annual increase of 40%. Now, in the last years, object storage has become one of the popular solutions for such scale-out use cases, and the industry produced tens of billions of dollars of revenue just in 2019. Unfortunately, object storage does not provide a typical file system interface, and as a result, many data-driven applications, for instance, are unable to use this new technology. Adapting the I/O layers of such applications is often very time-consuming and, depending on the application, not actually possible. So object storage file systems are a way to provide a file system interface on top of object storage so that applications can use this system. But while there exist many solutions, they have their limitations, particularly when we operate on large object store container with billions of objects that has become increasingly common in the past years. So with the flat namespace that object storage provides, container will become even larger in the future. And with DelveFS, we will show how the idea of a semantic file system can be used to reduce a very large container to only present a user with data they are actually interested in. But before I go into details with DelveFS, I want to go over 4 key terms that are relevant for this talk. First of all, DelveFS is an object storage file system, which simply provides a common file system interface on top of object storage. Many of those are available, but crucially, they only provide a very basic structure. So when they present objects as files, this is especially problematic if billions of objects are part in a single container. Now, semantic file systems are a way to bring order to the chaos in the sense that users only see information that they're interested in. And this has been a scientific topic for a number of years now, but they never have established themselves. Object properties are similar to extended attributes in file systems, and they are vital for further classification of objects beyond their name. Unfortunately, there's no or little support in object storage file systems, and if they are used, they can only be looked up via the extended attributes. Finally, event notifications are messages that describe changes in the object store. So for example, if an object is created, you could catch an event and process that. And they are only available in some object stores, for example, OpenIO or Google Cloud Storage. So for us, these event notifications are crucial to be able to provide a semantic file system onto an object store. And in fact, these events allow us to continuously update these semantic file systems in the background without actually requesting some new information from the object store. Of course, if you would do that, that would significantly impair the object store. Similar to other object store file systems, DelveFS is a fuse-based file system to provide a POSIX-like interface, and it can also be used while other object store file systems are used or the object store API directly. This is commonly known as dual access. Now, in the following, we call the semantic file system so-called views, and a user can create a definition of rules for this view, and then this view is unique to this user and will be updated accordingly in the future. And this is done by processing these event notifications, which is a specific component of DelveFS, and it will keep these views eventually consistent. In addition, if required, we have optional directory support, which we will talk later. And for that, we aim for several use cases, such as reducing the number of objects in huge containers. Now, previously I talked about billions of objects in a container, but this is already an issue if there are thousands or 10,000s of objects in a single container, where it is questionable if it is useful for a user in an application to list all of this information and then search for it. So in that sense, these rules that are defined in the views helps a user to access information that they are actually interested in. Further, which is very interesting for applications, a separate rule set directory can be created with specific rules. So any file that is added to that view and will correspondingly create an object will also be automatically classified by context. So a property would be attached to that, for example. Now for our architecture, we use the OpenIO object store, in our case in this work, because it emits the necessary events that we require, such as an event when a property is changed within an object. But in principle, because we're using the object store as a black box, it can also be replaced by another object store, such as Google Cloud Storage, although the specific support isn't implemented into DelveFS yet. So DelveFS is of two components. The first component is the DelveFS event handler, which is responsible for handling all of the events that are emitted by the object store, and then also applying all the events information to the specific rule set of the client's view. To store some of the object store's namespace, the event handler uses a KV store, which is RocksDB in our case. But it doesn't store the complete namespace, but only the namespace that is actually currently in use by the running views. This allows us to also discard some event information that would otherwise need to be processed. Now, the event handler is only a read-only medium for metadata information for the client. There can be multiple clients running at the same time, all with their unique views. But if an ls operation of a view is done, for example, it will always go through the event handler and lazily ask for that information. The event handler will not send a client information. Now, the client has a number of caches to reduce the strain on the event handler and also not to repeatedly ask for new data if, for example, you can just choose the checksum. But for writing and reading and for creating an object, the client will notify the object store directly. And like I said before, the application uses this client through a views library and can start and stop it at any time as a user. Now, these views are used by a user by so-called rule sets. And rule sets are basically just a number of rules within a file. We see this here on the left-hand side, where a user can specify which container they want to look at and what kind of properties they are interested for example. The specific name in line 9 and 2 are the specific rule set directory that the client will see, and this is also the name for it. Now, when the client first starts up, it'll send this rule set to the event handler, and the event handler will then either request the container's content from the object store, but if it's already available, it will just apply the rules stated in this rule set to this container and then respond with the corresponding metadata to the client, which makes the views available to the client. Now, later when the client is running, the event interface will continuously have events that the event handler will pull. So there's an ongoing event processing going on. This is up here. And also all the rule sets that are currently online by a client, these will be applied to each event that is incoming. So the DelveFS event handler always has the current information for a given view. So that leaves the client, when it, for example, does a lookup information and it is outside a specified caching time, the event handler can just respond with the current namespace information without contacting further components. Now, as mentioned before, we also offer directory support, which is in most cases not supported by object stores because they don't allow recursive containers in that sense. And they allow users to have further hierarchical structure on top of the rule set directories that they're given by our system. Now, these directories are optional, but they are also entirely virtual because the directory information is a part of an object itself. So we don't have specific junk directory objects that would store this information. But in any case, the directory information is always secondary, and they always must honor the rule sets first. And to show what I mean by that, we have an example here with two objects who have different colors. The first object color is black, the second is green, and they both are sitting within the same directory. So here you see that the directory information is part of the object. We have also three clients, all with their own unique namespace view. So for example, the first client is only interested in objects that have the color black or red. And because of that, it would only see the first object, while the third client sees both objects. Now, what would happen if the color of one of these objects is changed? Now, this can happen because in the object store API is used directly and the property is changed, or because a completely different file system client is changing that specific property. Then the views will be updated automatically by the event handler because it's processing the event and updates the views of all of those clients. So in this case, once these clients do an ls operation and they contact the event handler, the first client will realize that it has a new object because it now matches to its rule set that is red. Similarly, because there's no longer a green object within the object store, it is removed from the client 2 and 3. And similarly, if the directory information is changed because the first client is moving the first object into a different directory, which is then reflected as a property in the object, it will then move out for all clients. In this case, this is only relevant for the client 3. Now that you understand how rule sets work from a technical and user's perspective, I want to present a workflow which can be improved by rule sets, in this case a short read alignment in the biology field. And we use DelveFS to provide a publish-subscribe model. So in this case, the publisher produces scientific data in form of short reads and uploads this information to a container within object storage. And then a number of DelveFS clients that have unique rule sets defined, and thus they are interested in different kinds of objects of these short reads. They can then use this information to perform the short read alignment. Now they only have this information available that they're interested in, but previously, if a normal object storage file system client would be used, the whole container needs to be listed, and then you would need to search individually for objects that you're interested in. And this is especially problematic if we're working with a very large container, as we will see in the evaluation. Now, finally, we can have a separate rule set directory where the process data is placed into, and that has automatically some properties defined just because it's placed into there, which can be, for example, a different container here. So for the evaluation, we ran several experiments on the Morgan 2 supercomputer at Johannes Gutenberg University Mainz, where we ran an OpenIO object store that ran on 9 of those compute nodes. In addition, the DelveFS event handler also used the node local SSD that is used for the object store as an internal key value stored, but it's run on a different node, of course. We also have S3FS, another popular object store file system that is using OpenIO's S3 interface, and we will look at some metadata and data performance, and specifically directory listing performance. So for metadata performance, we created, removed, and started several thousand objects per process and compared DelveFS with the native interface of the OpenIO object store. And in this case, the goal for create and remove is to see the overhead that we add by just using a fuse-based implementation, because in the end, DelveFS also needs to use the object store API to create or remove an object. While in the beginning, the fuse-based overhead for one client node is rather large, we get into the metadata limit at around 8 nodes, where the object store and DelveFS performance is quite similar. Now for stats throughput, on the other hand, we do not contact the object store directly, but instead ask the event handler instead, because we need to see what kind of objects are part of our view. Now, in this case, the event handler provides massively increased performance, but this may also change depending on the load of the event handler. Now, for directory listing performance, we specifically wanted to look at how the file system behaves when we operate on a very large container with 100,000 objects in it, while compared with a smaller ruleset directory that is a subset of this large container and has just used 100 objects. In this case, the question is how can rulesets improve directory performance, and we compared this with the S3FS that is only able to operate on this large container of 100,000 objects. Now, there are two cases. First of all is the cold cache, where an ls command is previously not run of this directory. And as you can see, for S3FS, the time required for the ls is increasing continuously for up to 32 nodes and beyond. On DelveFS, on the other hand, there are multiple cases. So first of all, the second bar here is what happens if we do an ls on the large directory, and this operation has to be split up in multiple operations. So first of all, we also need to take into account how long it takes to scan this container on the event handler side, then to start up the client, and then also the ls time itself, which is the blue bar here. Now, if we just look at the smaller ruleset directory, this is then the third bar, we see that the time required to scanning the large directory of the event handler is predominantly using the time compared to actually using the ls on this small ruleset. Now, this is actually not shown here, which is why we go on this slide, where we zoom in a little bit on the 32 nodes case. And here we see on the third bar, the ls time required for the very small rulesets is very fast. And this actually stays the same on up to 128 tested nodes. So for the hot cache case, on the other hand, which means the ls is already previously run in the same environment, we see a similar picture. S3FS is continuously rising in runtime if using multiple nodes, while DelveFS stays stable. We show you up to 32 nodes, but we tested it up to 128 nodes and the runtime didn't change. But please also note here how the smaller rule set is significantly faster, even though we're still working on this very large original container of 100K objects. So for evaluating data performance, we compare the three systems that we have seen in these experiments, and we wrote and read 4 GB per process into the object store. And in this case, OpenIO is our upper bound, and DelveFS performs very closely to the abilities given by OpenIO, while S3FS falls a little bit short. The interesting part here is that the fuse-based overhead is significantly less prevalent in IO experiments than it is for metadata experiments, but this is also expected if we look at how the internals in Fuse work. Now, we ran this for up to 128 nodes, where the performance remained stable, but the IO performance, because we were using only SSDs, did not increase further of 60 nodes. S3FS unfortunately couldn't complete the experiments with 32 nodes and onwards. Now, to conclude, we have seen how DelveFS can use event processing so that the data is represented by context the way the users are interested in. Unfortunately, we couldn't talk about everything that we discussed in the paper, so I invite you to read that as well. In there, we also discussed more in detail how metadata and data communication works, and also have some evaluation about our event processing capabilities and latency, in which how long it takes until a change from the object store is seen within a client. Now, in the future, we want to work on several things. First of all, at the moment, the event handler is a single point of failure. While this is not directly impairing the clients, which just have to wait until the event handler is restarted, but unfortunately, the rule sets are currently not persisted within the event handler, and we want to work on that. In addition, we want to also create a distributed event handler so that a crash isn't necessarily halting the eventual consistency updates for a prolonged time. Further, we want to add support for additional object store interfaces such as Google Cloud Storage. Thank you very much.